Welcome back to Differential Calculus. In this video, I'm going to be going through some properties of functions. As has been the case for most of the course up to this point, I expect that most of the content we're going to be discussing in this video should be reviewed to most of you. For some of you, depending on the path that you've taken to get to this course, some of the vocabulary and notation might be slightly different from what you're accustomed to. And for some of you, it may have been a while since you've thought about some of these concepts. And so I want to make sure that everyone is on the same playing field and everyone is at the same point before we start getting into some of the more interesting ideas. So let me get my head out of the way and let's start off with the classic definition that a function is a rule which maps each element of one set, which we call the domain, to exactly one element of a second set called the codomain. And right there is the first place where this might seem a little bit strange to you, because many of you were expecting a different word there. I'll get to that different word in just a few moments. But before I get there, I do want to mention the notation F colon A right arrow B. This is the notation that I'm going to tend to use when I'm trying to talk about a function and define all of these properties a little bit more concisely. This notation tells us that a function which we are calling f maps from a domain which we are calling A to a codomain which we are calling B. Right? So just a very condensed way of explaining all of that information in a very small number of symbols. Now let's get to that other word that I mentioned that many of you were expecting. The range, or sometimes called the image of the function f mapping from A to B, is denoted and defined f of A, and it is the set of all elements y such that there is an x in A such that, ST is a nice abbreviation for such that in this context, y equals f of x. Right, so the domain, and I should have included in here, sorry about that. The domain is the set of elements y in the codomain, so that there actually is an x in the domain that gets there. Domain and range are the things that you are most accustomed to dealing with, and that is going to be the thing that we are dealing with by and large. The advantage of introducing this intermediate step of codomain is entirely one of convenience. Because I want to specify whenever I am talking about a function that we want a real valued function of one real variable. In this course, those are the only functions we're going to deal with. For those of you who continue onward into Calc 3, you start dealing with functions that are looking at other places. And even in Calc 2, you start to mention a little bit about integer variables and integer valued functions, anyone who's going onward to something like a discrete math course. But a real valued function of one real variable is a function whose domain is the real numbers and whose codomain is also the real numbers. I'm going to put an asterisk next to this R for the domain because we are going to deal with functions that are undefined at some points. And we're just going to be okay with that. We're going to be okay with something like f of x equals 1 over x is not well defined for x equals 0. But the distinction between codomain and range is important because for another example, f of x equals x squared, we want that to be a real valued function of one real variable. But one of the things you know about the squaring function is that the range of this function is from 0 to infinity. Right? The squaring function cannot produce a negative output if you give it a real numbered input. And so this is this situation that we want to be a little bit more careful about than you may have been in courses in the past. The range of this function is the positive real numbers, but the range is still a set of real numbers. It's just not a set of all of the real numbers. And that's why we introduced that terminology of codomain. The codomain gives us all real numbers, and the range is a subset of that that we can actually get to. Just by having that slight distinction, having that extra little bit of vocabulary, makes a lot of the things we want to do in this course just that little bit easier. A little bit easier to be more precise about what we're trying to say. I'm going to go through this pretty quickly. One of the things I want you to take away from this lesson is a family of some basic function shapes and also some names of some functions. I'm going to start with the simplest function that I can possibly imagine, which is the null function. The null function is the function f of x equals 0. You give it anything you want to give it, it gives you 0. The range of the null function is the singleton set containing just the number 0. All right. If I jump over to Desmos really quickly, we can graph the functions that we're going to be looking at. Helps if I can actually type. Let's try that again. There we go. F of x equals 0. We can see the nice horizontal line right across x equals 0. Nothing too exciting happening there. The unit function is not much more exciting. The unit function is the function f of x equals 1. The range of this function is the singleton containing just the number 1. The unit function is slightly more interesting because we can start to do stuff with it. If you multiply the unit function by some scaling factor, it will change what it looks like. If you multiply the null function by some scaling factor, it won't do anything at all. All right, but I can go over here real quick. I can replace my 0 with a 1. We can look at the unit function. It doesn't look that much different from the null function, but we can do it, and so we have done it. The identity function, f of x equals x. The range of this one is all real numbers. You know what the graph of y equals x looks like. It is the slant line at 45 degrees, but I can come over here real quick and I can graph that so we can see it on the screen. Again, nothing too exciting happening there, but it is something we can talk about, so now we've talked about it. The next most complicated function I can think of is the squaring function, f of x equals x squared. We just talked about this having a range from 0 to infinity, just positive numbers coming out. Again, you are familiar with the squaring function. There's nothing crazy happening here, but for the sake of completeness, I am going to go through and at least quickly show you the graph of all of these, if for no other reason than to get you comfortable looking at Desmos if you've not used that software before. I suppose I should mention at some point here that this software I'm using, Desmos, is a website that is available at zero cost. So type in the name of it, Desmos, DESMOS.com. It takes you to this website. It looks like this. You can start typing in equations. It will start producing the graphs. Nothing else to think about there. What other kinds of functions might be interesting? I should mention the cubing function. The cubing function is interesting because it takes us back to having a range of all real numbers. So the identity function has all real numbers, the squaring function has positive numbers, the cubing function has all real numbers again. If I jump back over to Desmos, I can replace the exponent 2 with a 3. We get the graph of the cubing function. Key features to note here, the way that the curve kind of jogs over near the origin is an interesting feature. You can see that showing up in other kinds of polynomial functions, and you've probably spent more time than you really feel like you should have on that in a college algebra or a pre-calculus course at some point in your previous mathematics education. Another function that I had mentioned previously is the reciprocal function. F of x is 1 over x. And the range here I'm going to write as x does not equal to 0 because writing it in interval notation, the interval from negative infinity to 0, union with the interval from 0 to infinity just looks really strange. Great, but I can come back over to Desmos. This one takes a little bit more typing. Get rid of that exponent. Let's put a 1 divided by instead. That didn't quite work. There we go. F of x is 1 over x. The graph of the reciprocal function forms a shape known as a hyperbola. Interesting features about a hyperbola are that it has horizontal and vertical asymptotes. Or in general, just a hyperbola has asymptotes going in several different directions. So we have an asymptote here. As we get smaller negative values of x, the graph comes as close to zero as possible without ever crossing the axis. The same thing happens over here for positive values of x. For values of x as near to zero as possible, when they are positive, the value of the graph goes upward towards infinity. When the values are near zero but negative, the values of the function go towards infinity. We'll be talking a lot more about that in the coming weeks, using the reciprocal function as our primary means of discussing the ideas of infinity and trying to take those and extend them to more general shapes is going to kind of be the theme of this first unit of the course. All right. The square root function is one that I do have to put a bit of an asterisk on, because this one I cannot get away with saying it's a real valued function of one real variable. The domain of the square root function is, of course, just the positive real numbers. The function is defined, f of x is the square root of x, and the range is also the positive real numbers. All right, but the square root function is just the parabola tilted onto its side. If I jump back over to Desmos, I didn't want my face in the way here. I just wanted the graph so that I can type. Right, another bit of a trick here. If you type the letters S, S, Q, R, T, it gives you a square root symbol. So I can graph the square root of x. Again, it's just a parabola that has been turned on its side. We can see a couple of interesting points, just like the parabola, it goes through 1, 1, maybe, close enough. And just like the parabola, it goes through, well, the parabola goes through 2, 4, the parabola on its side goes through 4, 2. And then 9, 3 instead of 3, 9, and so on. The last set that I want to talk about, I'm going to put these all on the screen at once, are the trigonometric functions. There are a number of trigonometric functions. Most students coming through a course in trigonometry or pre-calculus learn about 6 of them: sine, cosine, tangent, cotangent, secant, and cosecant. If your trig professor or your trig teacher was cruel, they might have shown you some of the others. There are, last I counted, there are 30 different trig functions that have been defined and used at some point in the past. Most of them are just not that interesting in today's world. We have calculators that can calculate things very quickly. So a lot of the other trig functions, things like the var sign, which is just 1 minus, I think var sign is 1 minus cosine, the havar sign, which is half of that, the covar cosine, which uses the sine instead of the cosine, and all this other stuff that happened is just take the trig functions and do a quick calculation on them. And it was very useful in the days when we had lookup tables, when the way to find the value of a trig function was to open up a book and flip to the page that had that function and look on the table for it. That's unpleasant to do, and we live in a world where scientific calculators exist and can do these things very quickly. That world hasn't been around for very long. Calculators able to do that sort of thing first came into existence in the 1980s. So it's been long enough that we can use them, and we've adapted and we've stopped teaching all these other things in trigonometry courses, but it's not like it's been around forever. Even at that, you know that you can figure out tangent by just taking sine divided by cosine. You can figure out you can figure out secant by taking the reciprocal of cosine. You can figure out cotangent by taking the reciprocal of sine. You can figure out cosecant by taking the reciprocal of sine. And so there's an argument that just sine and cosine is enough. I'm going to show you in this course that there are times when thinking about things in terms of just sine and cosine doesn't quite get there. We're going to use tangent and secant. It's not really going to come up in this course, but in the second semester of calculus, those two are going to be very useful and very important. I'll show you that there are corner cases where cotangent and cosecant are also important, but they are incredibly rare. And so I'm not entirely sure it's worth getting into all of the trig functions. So reducing the roster from 6 down to 4 gives us a little bit of a sigh of relief, a little bit less to worry about. All right, but let me jump over to Desmos once again real quick. And we can go through all of these types of graphs. Again, just typing out the name of the function. Sine of x gives you this nice periodic motion. Things to notice there. The maximum of the function is +1. The minimum of the function is -1. Sine has a range between -1 and +1. Cosine does much the same thing. Cosine is just sine shifted over a little bit. The tangent function takes on all possible values, but it has holes in its domain. Right? There are these vertical asymptotes all over the place. For example, this one at pi/2, where at that point, tangent is undefined. And then the really weird case, the secant graph, once again, not defined at pi/2, so that vertical asymptote is conveniently in the place. But the other weird thing is that between y equals 1 and y equals -1, the function cannot exist there either. The function is either bigger than +1 or smaller than -1. And so that gives us a couple of other interesting features to think about in these graphs and think about in the discussion. So if I just go through and list out all the ranges, sine and cosine are the interval from -1 to 1. Tangent has a range of all real numbers. And secant has this interesting range. In interval notation, it's from -infinity to -1. Then there's a jump. Then it goes from 1 to infinity. Sorry, those should be square brackets because +1 and -1 are included in that range. Another way that I sometimes think about the range, the range for sine and cosine is that the absolute value of y has to be less than or equal to 1. And the range for the secant is that the absolute value of y has to be greater than or equal to 1. So just another way of thinking about the same sort of thing. One last thing that I wanted to talk about in this lesson, and that is piecewise defined functions. You, once again, probably have seen a piecewise defined function at some point in a previous mathematics course, but they tend to be one of those things that pops up, you talk about briefly, and then they disappear. One of the big ideas in calculus, one of the big things we want to worry about in this course, is how to analyze a piecewise defined function more carefully. You don't spend very much time on them in the lower level classes, things like college algebra, because they get very messy very quickly. There's a lot of weird things that can happen, and so trying to describe them is an exercise at tearing your hair out. With calculus, we develop some of the tools that allow us to analyze a piecewise defined function more carefully and really dig in and allow us to use them effectively. So in general, a piecewise defined function is generally given as some operation. I'm going to stick with f of x because I'm boring like that. And then you get a giant brace. The size of it depends on how many pieces there are. I forgot to write down the first piece. I apologize. But you might have something like this. F of x is equal to -1. If x is less than 1, f of x is equal to x. If -1 is less than or equal to x is less than or equal to 1. And f of x is equal to 1 if x is greater than 1. I can graph this in Desmos, but I find that trying to do that is a little bit headache inducing. So let's just go ahead and graph this by hand real quick. F of x is -1, looks something like that. F of x is x, looks something like that. And f of x is +1, looks something like that. If I mark in and put those points in. This particular piecewise defined function is convenient because the two pieces match at the place where they break. Whether you take the first branch or the second branch at x equals -1, you get the same exact value out. That doesn't always have to be the case. Consider this function, g of x is equal to 2 if 0 is less than or equal to x is less than 2. G of x is equal to 1 minus x if 2 is less than or equal to x is less than 5. And g of x is equal to 0 otherwise. All right, let's sketch out a quick set of coordinate axes. And so if x, 0 is less than or equal to x is less than 2, the value of the function is 2. All right, so there's 0, there's 2. I've put an open circle at 2 to show that this function is not equal there, but everything up to not including. Right? The graph 1 minus x, I'm going to sketch in white really lightly because 1 minus x is a curve that looks kind of something like that. And we want to be there only for 2 less than or equal to x less than 5. All right, so there's 2 There's 5. There's the space in the middle. That's the part of the graph we're actually getting. And then 0 otherwise. Otherwise means all this stuff up here. Otherwise also means all this stuff over there. So you can use piecewise defined functions to get some very interesting looking things coming out of the graph. And that's where things are going to get very interesting for us. All right. So moving forward, playing with this sort of thing, playing with this sort of definition of a graph is going to be interesting. And using this along with some simple to understand pieces is kind of the way that calculus moves forward. Just to make sure that everyone is comfortable with these ideas of piecewise functions, here's a problem for you to spend a little bit of time thinking about. I'm just going to copy this same g of x we were working on somewhere I can get a little bit more space. Okay, it wants to be there, it'll be there. What I'd like you to do, very simply, is evaluate this function at 5 points. I'd like you to evaluate g of -1, g of 0, g of 2, g of 4, and g of 5. All right, take a few minutes, see what you can do with that. Again, I hope that this is familiar to you, but just a quick check to make sure that everyone remembers how these things work, and I'll see you in the next video.